Hey everybody, it's Dr. J, and today we are talking about acid and bases. Let's talk about chemistry. All right, so real fast, we about to give you three definitions that you should know for acid and bases, okay? So technically all these are correct, right? They're just a different way of saying what an acid or base is. So the first one is Arrhenius definition. So this was basically the very first definition of an acid and base. Okay, essentially, an acid was basically increasing your H plus concentration. So with Arrhenius definition, we had to realize that this is very specific. Okay, even if we look at our base, increase OH concentration. So what's missing on this part is that basically with this definition Arrhenius had, he also said that it had to be in an aqueous solution. Okay, while producing H plus or OH ions. Right. So this was very limited to what we consider to be an acid or base, right? We couldn't consider other things. Next, we have Brønsted-Lowry. All right, this happened in 1923. He came around, right? They came around, I should say, and they basically broadened our definition of what we consider the acid and base to be. Okay, so basically, they said acids donate H plus or protons, right, and bases accept protons. All right, so if you hear me say a proton going forward, just know that proton, I'm talking about a hydrogen. Okay, and that's a key difference between Bronsted-Lowry and Arrhenius, right? Arrhenius super specific. You got to have H plus ions or OH ions, and then you got to be in an aqueous solution. You got to be very specific. This is an acid and base. Bronsted-Lowry, we open that up a little bit. So now we're saying, okay, either you donate or you accept. That's how we know you are a acid or base. Now, lastly, we have Lewis. So these are basically where your acids are now. Now we're into electrons. Okay, so now your acids are accepting electrons. Okay, so if you are accepting electron, you are acid. And if you are a base, you are going to be donating your electron. So we can see right now, this has really broadened the spectrum as far as what we consider to be an acid or base. Okay. So these are all definitions of acid and bases. All of them are correct, right? It's just a different way of saying them. So speaking of acid and bases, there is one substance that can act as both an acid or base. So let's talk about water, right? Water is always up to doing something. Okay, so in this case, water has some ionic character. So when you go, in this case, we look at this equation over here, we combine waters together. There's a chance that when this happens, you could form an H3O plus ion and an OH ion, right? In this case, you are taking that extra hydrogen and adding on to here and then taking away that hydrogen from our OH. So when this happens, basically, this is what we have here. This water can be a conjugate acid and a conjugate base. So these are going to be very important terms you want to know going forward, right? Which we'll talk more about these in upcoming videos. But for now, just understand that water, right, can have both an acid and a base. And we call this process self-ionization. Okay, this is self-ionization. Okay, so basically, this is what water can do. Right. And then one more thing. Um, if you ever see this H plus, this H plus stands for H3O plus. Okay. This type of ion, this cation right here. Or it could be this H9O4 plus. To where basically we got some intermolecular forces happening between our H plus and then those extra water molecules going on. So basically, this is where we get this hydrated proton here. Because we understand that water is self ionization, we can actually use that towards our benefit. In this case, let's talk about K. All right, so this is all about acid base equilibrium. We got to understand that if our K, right, KEQ, that's our equilibrium constant. Basically, we understand, right, from our previous videos. Check those previous videos, see if you need more understanding. But this is products of a reactants. Taking our H plus and OH, putting it over water, H2O. And in this case, guess what we notice, everybody? What do we notice, right? Water is a pure liquid. For pure liquids, they are not going to impact our equilibrium. So therefore, our K is actually H plus and OH. We can use, in this case, KW. So KW is going to indicate water self or auto-ionization, which we talked about before, right? The concept of water being a conjugate acid and a conjugate base at the same time. All right. But please understand, KW is still K at the end of the day. Okay. How we talked about K equilibrium or KC, right? It's just a new subscript for our K. All right. But it's still equilibria at the end of the day. And I have listed here some more equilibria we will be talking about going forward in the upcoming videos, Ka, Kb, and Ksp. Right? In this case, the subscripts are just changing depending on what you have here. So as we said, with Kw, that's water, Ka, that's acid, right? Just depends what we're working with. But with Kw, we got to understand that Kw equals H plus and OH minus. Okay? Now, one thing we need to understand as well is, well, Kw, we actually know the value of Kw this time. Kw is 1 times 10 to the negative 14 at 20 degrees Celsius. And if Kw is this value, then essentially our acid concentration and our OH concentration equal 1 times 10 to the negative 14. So if it equals 1 times 10 to the negative 14, that means that both of our concentrations got to equal half, right? So in this case, H plus and OH, right, these ions in pure water will equal 1 times 10 to the negative 7, right, molar.